Every single star you see began as a faint, random flicker in the void. Those brilliant lights in the night sky owe their existence to quantum whispers, the most delicate events in the subatomic realm. By the end of this journey, you will understand how these microscopic murmurs designed the entire cosmos. We will uncover how a universe that started perfectly smooth could ever grow galaxies, and why the specific pattern of stars above you was decided by pure chance at the dawn of time. What does our vast, structured universe suggest about its unpredictable beginnings? This initial uniformity presents a profound puzzle. How could a cosmos so perfectly smooth and featureless ever give rise to the sprawling cosmic web of galaxies and the vast empty voids between them? The answer lies in the nature of that early plasma. For several 100,000 years, the universe was far too hot for atoms to form. Light could not travel freely. It was a thick, glowing fog, a cosmic broth where photons of light constantly bounced off a sea of free electrons and protons. This was a state of near-perfect equilibrium, a blindingly bright and uniform soup with no distinct regions of higher or lower density. Yet, hidden within this apparent perfection were the faintest of imperfections, tiny quantum ripples that would one day become everything. That initial, perfect smoothness was an illusion. For a tiny fraction of a second after everything began, the cosmos was not just expanding, it was inflating, stretching at a rate far beyond the speed of light itself. This was not a gentle growth, but a violent, exponential surge that took a region smaller than a single proton and blew it up to a size larger than our entire observable universe. Within that furious expansion, the stage was set for the first quantum whisper. The vacuum of space itself was not truly empty. It was a seething, bubbling sea of potential, where pairs of virtual particles and antiparticles flickered in and out of existence, borrowing energy from nothing for the briefest moments allowed by physics. These fleeting energy shifts, these random fluctuations in the fundamental quantum fields, were the original murmurs. They were unimaginably small and utterly random, insignificant on their own tiny scales. But then inflation did something miraculous. It grabbed hold of these subatomic jitters and stretched them, magnifying them across the vast, newly born cosmos. A random quantum flicker that was once smaller than a single particle was suddenly blown up to span light years. This fantastic stretching process imprinted a faint pattern of slightly denser and slightly less dense regions onto the fabric of the universe. These were the first imperfections, the first seeds of structure. That random quantum static became a cosmic blueprint, a direct and permanent link between the unpredictable world of the very small and the grand architecture of everything we see in the night sky. These amplified quantum ripples, now stretched across the cosmos, were not yet stars or galaxies. They were simply subtle differences in density, tiny hills and valleys in the fabric of space. For hundreds of thousands of years, these seeds lay dormant, trapped within a universe too hot and dense to allow them to grow. The entire cosmos was a glowing, opaque plasma, a churning sea of matter and energy where light was constantly scattered, unable to travel in a straight line. Then a pivotal moment arrived, an event cosmologists call recombination. The universe had expanded and cooled enough for electrons and protons to finally combine into stable, neutral hydrogen atoms. In an instant, the fog lifted. The universe became transparent, and for the first time, light could travel freely across vast distances. That first burst of liberated light is what we detect today as the cosmic microwave background. It is the oldest light in existence, a fossil imprint from the infancy of everything. This cosmic afterglow is not a perfectly uniform glow. When we map it with incredible precision, we see a mottled pattern of tiny temperature variations, a tapestry of slightly warmer spots and slightly cooler spots. These are not random imperfections. Each of those hot and cold spots is a direct imprint of those original quantum whispers. Where the early universe was slightly denser, thanks to an inflated quantum fluctuation, gravity had a slightly stronger pull. This required photons of light to expend more energy to climb out of that gravitational well. And in doing so, they lost a tiny amount of energy, shifting to a slightly cooler temperature. The slightly less dense regions, the valleys, had weaker gravity, allowing light to escape more easily, remaining a bit warmer. The specific pattern of these hot and cold spots, their size and distribution, matches the prediction of quantum fluctuations stretched to cosmic scales. It is the universe's baby picture, and it shows the exact blueprint for all future structure. The statistical properties of this pattern are the smoking gun. The distribution of these temperature differences follows a very specific, predictable signature that points directly to a quantum origin. It is a fingerprint left by the uncertainty principle itself, a hallmark of randomness that was baked into the cosmos at the moment of inflation. This cosmic snapshot provides the most compelling evidence we have that the grand architecture of the universe, the great walls of galaxies and the immense voids between them, was seeded by the most humble and unpredictable of events. It forges an unbreakable link between the ghostly rules that govern particles and the majestic evolution of the entire cosmos. So the next time you gaze up at the night sky, remember that the specific arrangement of stars and darkness was not preordained. It was a cosmic lottery, and the winning numbers were drawn by quantum chance. Those faint blueprints in the cosmic afterglow were just the beginning. For the grand structures of the universe to emerge, those subtle whispers needed a powerful amplifier. That force was gravity. Think of those slightly denser regions as gentle dips in the fabric of space. A tiny bit of extra matter meant a slightly stronger gravitational pull, an invisible hand that began to slowly gather more material from its surroundings. Over hundreds of millions of years, this process created a cosmic feedback loop. A region starts with a minuscule overdensity, a mere 1% more matter than its surroundings. That small excess pulls in a little more gas and dark matter. With more mass, its gravitational pull grows stronger, allowing it to attract even more material from a wider area. This slow, patient accumulation is what transformed a faint quantum imprint into a massive, collapsing cloud of gas, a protogalaxy. Without gravity's relentless and patient pull, those initial quantum ripples would have remained as insignificant as faint wrinkles on the surface of a vast ocean, never coalescing into anything more. They would have faded into the background hum of the expanding cosmos. This partnership between the quantum and the classical is fundamental. The random quantum fluctuation provided the creative spark, the element of chance that broke the perfect symmetry. But it was gravity, a predictable and powerful force, that took that spark and nurtured it, building it up over cosmic time into the brilliant structures we see today. The existence of every galaxy, every star, and every planet relies on this incredible collaboration between the unpredictable whisper of the quantum world and the steadfast, gathering hand of gravity. But there was another, invisible actor waiting in the wings. A crucial player in this cosmic story is dark matter, the mysterious substance that makes up most of the mass in the universe. Unlike the atoms that make up stars and planets, dark matter does not interact with light at all. It is completely invisible, passing through you and everything else like a ghost. But it does feel gravity's pull. When those initial quantum ripples were stretched across the cosmos, they created tiny overdensities in both regular matter and this mysterious dark matter. This is where the story takes a critical turn. For hundreds of thousands of years, the normal matter, the protons and electrons, were trapped in a constant battle with light. The intense radiation pressure from the searing plasma pushed back against gravity, preventing the gas from collapsing easily. It was like trying to build a sandcastle in a stormy sea. Dark matter, however, was immune to this pushback. Since it does not interact with light, it felt only the gentle, persistent tug of gravity. This gave it a monumental head start. While normal matter was still being buffeted by radiation, the dark matter was quietly, invisibly gathering itself. Its subtle clumps began to coalesce first, forming vast, invisible gravitational wells long before the first stars could ever ignite. These dark matter halos became the unseen scaffolding for the entire visible universe. They were the hidden frameworks, the cosmic skeletons upon which the flesh of galaxies would eventually be draped. When the universe finally cooled and became transparent, ordinary gas, now freed from the pressure of radiation, began to flow into these pre-existing gravitational pits. The quantum whispers had already drawn the map, and dark matter had built the gravitational highways that guided the normal matter to its destination. This invisible architecture accelerated the entire process of galaxy formation, pulling gas in to create the brilliant, dense knots of light we now see. So the specific pattern of galaxies across our night sky is a direct tracing of that underlying dark matter distribution, which was itself dictated by those first quantum murmurs. The grand design of the cosmos was drawn first in the invisible, then filled in with light. This cosmic lottery did not just draw the map for galaxies. It also determined the very chemistry of creation. Within the first few minutes of the universe, an incredible alchemy was underway. The entire cosmos was still a searingly hot nuclear furnace, a dense, churning plasma of fundamental particles. In this inferno, protons and neutrons collided and fused, forging the first atomic nuclei in a furious burst of activity known as Big Bang nucleosynthesis. For a brief window of time, the universe was hot enough to act as its own particle accelerator, creating the primordial ingredients for everything to come. The outcome of this process was not perfectly uniform everywhere. The rates of these nuclear reactions depended critically on the density and temperature of the plasma at any given point. And these local conditions were not identical. They were imprinted with the faint, amplified signatures of those original quantum whispers, where a quantum fluctuation had created a region of slightly higher density. The nuclear reactions proceeded at a marginally different pace. This led to tiny, patchy variations in the abundance of the lightest elements. One region of the early cosmos might end up with a barely perceptible fraction more helium, while another had a trace more lithium, all woven into a vast, primordial tapestry of hydrogen. Think of it as a cosmic baker making a colossal batch of bread. If the mixture is not stirred with absolute perfection, some pockets will have a little more salt, while others have a bit more yeast. On the scale of a single loaf, this is insignificant, but on the scale of the entire universe, these slight imbalances in the recipe became permanent. This means the fundamental building blocks for future stars, planets, and even life itself were not distributed with perfect uniformity. The quantum whispers, amplified to cosmic scales, had already begun to season the cosmic broth before the first star ever ignited. The specific chemical foundation upon which entire galaxies would later build their stellar populations was subtly, yet irrevocably, shaped in those first fiery minutes. The stage was not only set for structure, but also for a specific and varied chemistry, all dictated by the random hand of quantum chance. These dark matter scaffolds and chemically varied clouds set the stage for a final, brilliant act. Deep within the immense gravitational wells of those invisible halos, vast clouds of hydrogen and helium began to collapse. As these protostars condensed, they faced a critical problem. A spinning cloud of gas possesses a property called angular momentum, much like a figure skater pulling in her arms to spin faster. To shrink from a diffuse cloud into a dense, hot star, this spin had to be shed, or the cloud would simply fly apart. The solution arrived through magnetism, the universe's very first magnetic fields, faint traces woven into the cosmic fabric. are thought to have been generated by quantum processes in its earliest moments. These primordial fields provided the necessary leverage, channeling material and allowing the infant star to slow its spin and continue its gravitational collapse. Without this quantum contribution to magnetism, the first stars might never have condensed tightly enough to ignite, and then came the moment of true creation. At the star's core, temperatures and pressures soared to unimaginable levels, yet even under these extreme conditions, a fundamental barrier remained. Protons, the nuclei of hydrogen atoms, all carry a positive electrical charge, and similar charges violently repel each other. The temperature at the core of a young star is still not nearly high enough to force these protons to collide and fuse with pure, classical force. They need a secret passage. This is where the most profound quantum whisper of all comes into play, a process known as quantum tunneling. In our everyday world, you cannot walk through a solid wall. In the quantum realm, particles like protons are not just tiny balls. They are also smeared-out waves of probability. There is a small but real chance that a proton can simply appear on the other side of that seemingly impenetrable electrical barrier, as if it tunneled right through it. This is not a theory. It is the fundamental mechanism that powers every star in the universe. The brilliant ignition of the first starlight, that monumental moment when the cosmic dark was finally pierced, was not a classical certainty. It was a probabilistic event, a direct and stunning consequence of quantum uncertainty operating at a stellar scale. The nuclear fires that forged the heavier elements that lit up the cosmos and made life possible were born from a subatomic gamble. Every star you see shines because the rules of the very small allowed it to cheat a fundamental force of nature. That same quantum gamble that ignited the stars also forged the very substance of our world. Deep within a star's core, the fusion process is a relentless chain of quantum tunneling events. One proton tunnels to meet another, forming helium. Helium nuclei then tunnel into one another, creating beryllium, and so the chain continues, building elements like carbon and oxygen in a step-by-step ascent up the periodic table. This is stellar alchemy, a slow and steady cooking process that powers a star for millions or even billions of years. But this process has a fundamental limit. The creation of elements stops at iron. Fusing atoms to make anything heavier than iron does not release energy, it consumes it. So how did the gold in a wedding ring or the uranium in a power plant ever come to be? The answer lies in the most violent deaths in the cosmos. When a truly massive star exhausts its nuclear fuel, its core collapses in a fraction of a second. The resulting shockwave rips the star apart in a cataclysmic supernova explosion. For a few breathtaking moments, the conditions become so extreme that a frantic new process takes over: rapid neutron capture. In this stellar inferno, a torrent of free neutrons floods atomic nuclei. There is no time for slow, stable decay. Nuclei must capture these neutrons in rapid succession, a process entirely governed by the quantum properties and stability of atomic structures. This is how all the heavy elements, from silver and iodine to lead and gold, are forged in a single, spectacular blast. The supernova then scatters this newly created elemental dust across interstellar space, seeding future generations of stars and planets. And here is the profound connection. Where did these enriching supernovae occur? They did not happen uniformly. They exploded most frequently within those early regions of slightly higher density, the same hills in the cosmic landscape that were originally mapped by quantum whispers. The very distribution of the elements essential for rocky planets and for life itself was channeled along those ancient, invisible lines. The specific chemistry of our solar system, the abundance of iron in our blood and calcium in our bones, was not a universal constant. It was a local outcome, a gift from long-dead stars that themselves formed because of a random quantum fluctuation in the first instant of time. Our planet's diversity and the chemistry within us is a direct inheritance from the primordial quantum static. Our planet's unique chemistry was forged in stardust, but its very existence required a stable home. Around a newborn star, a vast, spinning disk of gas and dust begins to coalesce. This protoplanetary disk is a chaotic nursery, the birthplace of future worlds. Within this swirling maelstrom, the first step toward building a planet seems almost impossibly humble. Tiny specks of dust, finer than smoke particles, drift through the void. For them to become anything more, they must first stick together. This is not a simple collision. At the atomic level, the surfaces of these grains are governed by the strange rules of quantum chemistry. Electrons from one grain can interact with the electrons of another, creating fleeting, attractive forces. These weak quantum bonds allow the microscopic particles to cling to one another, building up slowly from dust to pebble, and from pebble to rock. Without this subtle quantum handshake occurring trillions upon trillions of times, the very foundation of planet formation would fail. The initial architecture of this stellar nursery is far from uniform. As we observe these disks around other stars, we see they are not featureless platters of material. They are structured, etched with bright spiral arms and dark, empty gaps. These are density waves, areas where the disk's material has been gathered up or cleared out. What creates these patterns? Often, the gravity of a nearby star or a massive planet already forming within the disk can sculpt these waves, acting like a spoon stirring coffee and creating ripples. This is where the cosmic chain of causality reaches its culmination. The gravitational environment that stirs a specific disk, the very presence of that stellar companion or the location where a giant planet first coalesces, is not random. It traces back to the initial overdensity of the star's parent gas cloud, which was shaped by the dark matter scaffolding, which was itself dictated by the primordial quantum ripples. The specific arrangement of planets in any solar system, the location of a rocky world within its star's habitable zone, the timing of its formation, all of these critical factors are guided by gravitational patterns imprinted billions of years earlier. The existence of our own Earth, orbiting at just the right distance from a stable star, was not a guaranteed outcome of a uniform universe. It was a possibility carved out by a specific gravitational landscape, one that was drawn by the faintest of quantum whispers at the dawn of everything. The magnificent spiral arms of a galaxy are not fixed pinwheels of stars, but more like a cosmic traffic jam moving through a bustling city. Stars, gas, and dust continuously flow into these dense waves, are temporarily slowed down within them, and then pass through on the other side. It is the wave itself that persists, a pattern of compression traveling around the galactic disk. The birth and longevity of this beautiful structure depend on the precise way the galaxy first came together. The initial spin of the vast protogalactic cloud, its total mass, and its specific distribution of material, these were the starting parameters for the entire system. And these parameters were not chosen at random. The cloud itself collapsed within a specific, pre-existing gravitational well, a particular valley in the cosmic landscape that was carved out by the amplified quantum ripples from the dawn of time. A slightly deeper gravitational potential might have led to a cloud with more angular momentum, spinning just fast enough to form a delicate, grand design spiral. A shallower well might have resulted in a cloud that collapsed more directly, creating a smooth, elliptical galaxy with little rotation. The stunning diversity of galactic shapes we observe through our telescopes, from the stately whirlpools of Andromeda to the chaotic irregularity of the Magellanic Clouds, can be traced back to the unique gravitational environments of their birth. Each galaxy's architecture is a final macroscopic expression of a microscopic quantum origin. The grand design of a spiral arm, a structure spanning tens of thousands of light years, is the ultimate magnification of a whisper from the quantum void. Zoom out far enough, and the universe reveals its final, breathtaking structure. Galaxies are not scattered randomly like stars in the sky. Instead, they are gathered into a colossal architecture, a luminous web of interconnected filaments that stretches across billions of light years. These great walls of galaxies surround vast, nearly empty voids, creating a cosmic sponge of staggering proportions. This is not a chaotic arrangement. It is a direct, predictable outcome of the gravitational forces that have been at work for over 13 billion years, sculpting the initial quantum blueprint. The universe on its largest scale is a single, interconnected network, and its design was locked in from the very beginning. How can we be so sure that this immense cosmic web was born from quantum whispers? The proof lies not just in our telescopes, but inside our most powerful computers. Cosmologists create virtual universes in their supercomputers, starting with nothing but a smooth, expanding space. They then introduce a single ingredient, a Gaussian random field of tiny density fluctuations. This is a very specific type of randomness, a statistical fingerprint that is the hallmark of quantum processes amplified by inflation. There are no galaxies, no stars, no pre-built structures in this initial digital cosmos. There is only gravity and that faint, random seed. The simulation is set in motion, and the virtual eons fly by. We watch as gravity begins its patient work, pulling matter ever so slightly toward those regions of higher density. The tiny hills in the density field grow into gentle mounds, then into pronounced peaks. The valleys, meanwhile, are evacuated as matter drains away toward the emerging structures. Over billions of simulated years, the random noise organizes itself. It weaves an intricate pattern of filaments and knots, with immense empty spaces opening up between them. The final result of the simulation is unmistakable, a cosmic web that looks identical in its essential architecture to the one we map in our real night sky. This is a profound validation. The specific superclusters, the dense nodes where thousands of galaxies swarm together, were not placed there by chance. They mark the spots where the most pronounced quantum whispers occurred. The great voids, those dark and empty deserts spanning hundreds of millions of light years, are the legacy of the broadest, most under-dense quantum valleys. Every feature in this grand design, from the thickest filament to the most isolated galaxy, is a direct descendant of a random subatomic event. The entire visible universe, in all its structured splendor, is the magnificent echo of a quantum murmur. This invisible web of matter and light is not the only structure woven into the cosmos. Look deeper, and you will find another force, a subtle presence that guides the flow of gas and steers the paths of high-energy particles. Magnetic fields stretch between the stars and coil within galaxies, an unseen cosmic architecture. We know they are there because we can see their influence, but their origin story is one of the great lingering puzzles. How did these vast, organized magnetic fields, spanning tens of thousands of light years, first come to be? The leading clue points us back once more to the universe's first moments. One compelling idea suggests that during the violent expansion of inflation, or perhaps during a later phase transition as the cosmos cooled, the fabric of reality itself was stirred by quantum turbulence. Just as the random motion of electrons in a wire can create a small magnetic field, these primordial quantum jitters could have generated the faintest magnetic whispers. These would not have been the powerful fields we detect today, but rather the most humble seeds, imprinted on the universe when it was just a fraction of a second old. For these seeds to grow into the cosmic forces we observe, they needed a powerful engine. That engine is the motion of ionized gas. Across the universe, vast clouds of plasma swirl and churn, conducting electricity. When a moving, electrically conductive fluid interacts with even a tiny magnetic field, it can stretch, twist, and amplify that field in a process known as a dynamo. Think of a simple bicycle dynamo, where the spinning of a wheel generates a small electrical current that powers a light. Now, imagine that process on a galactic scale, with the slow, majestic rotation of an entire galaxy acting as the wheel, and the seething plasma between the stars as the conductive wire. Over billions of years, this cosmic dynamo could have taken those quantum seeds and amplified them into the immense magnetic structures we now detect, structures that themselves play a vital role in the birth of new stars. The very fields that help gather gas to form stellar nurseries may have begun as a random tremor in the quantum fields of the infant universe. The magnetic map of the cosmos could be the final, magnificent echo of a whisper from the dawn of time. The steady glow of our sun, a comforting presence in the sky for billions of years, is a testament to a delicate quantum balancing act. This reliable shine is not the product of a simple, brute force fire. It is a controlled nuclear burn, its pace meticulously regulated by the same probabilistic process that first ignited it. At the star's heart, protons must continually overcome their powerful electrical repulsion to fuse into helium. The core temperature, while unimaginably hot to us, is still far too low to provide the classical energy needed for this to happen consistently. The star's entire existence hinges on quantum tunneling. The rate at which protons successfully tunnel through their mutual barrier dictates everything. It controls the speed of the nuclear reactions, which in turn determines how much energy the star produces each second. This energy output creates an outward pressure that perfectly balances the star's immense inward gravitational pull. It is this quantum-regulated equilibrium that grants a star like our Sun its remarkable stability and longevity, shining steadily for over 9 billion years. Without the precise probability of quantum tunneling, this balance would be impossible. The star would either flare up violently and burn out in a cosmic blink, or it would fail to ignite properly, collapsing back into a cold, dark cloud. The very fact that we have a stable, long-lived star to warm our world is a direct consequence of the quantum rules governing its core. This delicate dance between probability and gravity writes the final chapter for every star. When a star finally exhausts the hydrogen fuel in its core, this balance is shattered. The core contracts under gravity's renewed assault, heating up until it can begin fusing heavier elements like helium into carbon. Each new stage of fusion relies on a different quantum tunneling probability, setting a new timer for the star's life. The ultimate fate of the star, whether it ends its days as a dense white dwarf, a city-sized neutron star, or collapses into a black hole, is preordained by its initial mass. Yet the journey to that fate, the very length and nature of its stellar lifetime, was paced at every step by the quantum whisper of tunneling. The brilliant, stable light that has bathed planets and enabled life across the cosmos is not a simple classical flame. It is the glow of a trillion quantum gambles, paying off in perfect harmony second after second, for eons on end. The same quantum rule that gives our world its solidity also writes the final chapter for most stars. Every white dwarf is a stellar ghost, the exposed core of a star like our Sun that has shed its outer layers. What remains is a sphere of matter roughly the size of Earth, yet containing a mass comparable to our stars, crushed to an almost unimaginable density. A single teaspoon of this material would weigh many tons on Earth. Under such an immense gravitational crush, all classical forces have long since been defeated. The nuclear fires are extinguished, and the heat pressure that once balanced gravity is gone. So why does this incredible object not continue to collapse into an even denser state, or simply vanish into a point? The answer is not a force in the classical sense, but a quantum refusal. It is a fundamental no, a law of physics that simply will not be broken. This is the Pauli exclusion principle. In the subatomic world, electrons are not just tiny particles. They carry a kind of quantum identity, a set of properties known as quantum states. The Pauli exclusion principle states, with absolute authority, that no two electrons in the same system can share the exact same set of these quantum properties. They cannot occupy the same state. It is as if every electron in the universe demands its own unique seat in a cosmic theater. In the heart of a white dwarf, gravity has squeezed the star's electrons into an incredibly small volume. They are packed together with almost no space left, but the Pauli principle forbids them from all crowding into the lowest energy state. They are forced to stack into higher and higher energy levels, creating a tremendous outward pressure known as electron degeneracy pressure. This pressure does not come from heat or motion or chemical bonds. It is a purely quantum mechanical force, a direct consequence of this single, unbreakable rule. It is the universe itself saying that matter simply cannot be compressed beyond this point. This quantum standoff is what gives a white dwarf its final, permanent form, supporting it against the unrelenting pull of its own gravity for trillions of years to come. These faint, dense cinders that litter our galaxy are not held up by fire, but by a fundamental quantum law written into the fabric of reality. But for stars born with even greater mass, this quantum standoff escalates into something far more extreme. When a truly colossal star ends its life in a supernova, the remnant core is crushed with such ferocious force that even electron degeneracy pressure shatters. The collapse does not stop. Gravity overwhelms every barrier, forcing electrons and protons to merge in a violent transformation, canceling their charges and creating a sea of neutrons. The result is a neutron star, a city-sized object containing more mass than our entire sun. A single sugar cube of this material would weigh as much as every human on Earth combined. This is no longer familiar matter. A neutron star is, in essence, a single gargantuan atomic nucleus, a perfect sphere of pure neutrons bound by gravity. What holds this incredible object up against its own unimaginable weight? It is, once again, the Pauli exclusion principle, but now applied to neutrons. Just as electrons refuse to be squeezed into the same state, these densely packed neutrons generate an even more powerful neutron degeneracy pressure, creating the final, ultimate line of defense against total gravitational collapse. The entire structure of a neutron star is a quantum artifact. Its interior is a realm of bizarre states of matter that we cannot recreate on Earth. The intense pressure may crush the material into a superfluid, a substance with zero friction that can flow without losing any energy, or into a solid crust of exotic nuclei arranged in a perfect, immense crystal lattice. And then there are the magnetic fields. A neutron star can possess a magnetic field trillions of times stronger than Earth's, a force so powerful it can distort the shape of atoms themselves. These fields are often channeled through narrow beams at the star's magnetic poles. As the neutron star spins at dizzying speeds, sometimes hundreds of times per second, these beams sweep across space like a cosmic lighthouse. When a beam flashes across our telescopes, we see a pulsar, a perfectly timed, blinking beacon in the darkness. Every pulse of light from a pulsar is a direct signal from this quantum world. The precise timing of its flashes is governed by the star's rotation, which is itself stabilized by the quantum rigidity of its degenerate core. The intense magnetic fields are likely the amplified remnants of the original star's field, twisted and concentrated during the collapse into a quantum-scale phenomenon writ large. These stellar cinders are not just dead stars. They are the universe's most extreme laboratories, places where the rules of quantum physics are tested under conditions of unimaginable density and force, demonstrating once again how the smallest laws sculpt the most colossal and exotic objects in the cosmos. Even the neutron star's quantum defiance has its limits. If the remnant core is too massive, a final, terrifying collapse begins. No force in the universe can stop it. Not nuclear fire, not electron degeneracy, Not even the immense pressure of packed neutrons. Gravity wins its ultimate victory, crushing the core into a region of infinite density, a singularity. Surrounding this point of no return is the event horizon, a perfect, one-way boundary in space-time. Once anything crosses this threshold, it can never come back. Not even light itself can escape. This is a black hole, the most extreme object predicted by Einstein's theory of gravity. Yet, this classical victory creates a profound conflict with the quantum world. According to the fundamental rules of quantum mechanics, information can never be truly destroyed. If you burn a book, for example, its information is not lost. In principle, a being with perfect knowledge could trace the smoke and ashes backward to reconstruct every word. The universe, in the quantum view, never forgets. But a black hole seems to break this sacred rule. Anything that falls in, whether a book, a star, or an entire spaceship, carries information with it. According to classical general relativity, that information is irretrievably lost behind the event horizon, sealed forever in the singularity. This sets up a direct contradiction, a battle between our two most successful theories of physics. The conflict deepens with a stunning discovery. Black holes are not completely black. Due to wild quantum fluctuations right at the edge of the event horizon, they can slowly evaporate. This is Hawking radiation. Imagine the vacuum of space near the horizon, fizzing with pairs of virtual particles and anti-particles, constantly flickering in and out of existence. Normally, these pairs annihilate each other almost instantly. But if one particle of the pair falls into the black hole just as its partner escapes into space, the black hole loses a tiny amount of mass. Over eons, this quantum whisper at the boundary causes the black hole to shrink and ultimately vanish. The problem is what happens to the information. The Hawking radiation that leaks out is completely random, a featureless thermal glow. It carries no details, no fingerprint of what fell in. When the black hole finally evaporates, all the information about the objects that formed it seems to have been erased from the universe. This is the information paradox, a glaring sign that our understanding of reality is incomplete. The resolution must lie in a deeper theory, one that unites gravity with quantum mechanics. Perhaps the event horizon is not a smooth, classical surface, but a seething firewall of quantum energy. Maybe information is not lost inside, but is somehow scrambled and encoded onto the surface of the horizon itself, projected like a hologram. Or perhaps the very concepts of location and information break down in such extreme gravity. The existence of black holes forces us to confront these possibilities. They are not just cosmic vacuum cleaners. They are laboratories that test the limits of physics, pushing us to see how the smallest quantum whispers might ultimately govern the fate of spacetime itself. That brilliant point of light you see from a distant star has completed an incredible quantum journey to reach you. It begins deep within the star's fiery atmosphere, where atoms are constantly being jostled and energized. An electron orbiting an atom's nucleus absorbs a burst of energy and is knocked into a higher, unstable orbit. It cannot remain there for long. In a fleeting moment, it falls back down to its original state, and as it drops, it releases the excess energy in a precise packet. A single quantum of light we call a photon. This is not a smooth, continuous flow. It is a staccato burst of pure energy, a discrete jump between two distinct levels, like a ball clicking down a set of fixed steps. Every gleam of starlight is born from trillions upon trillions of these individual quantum transitions, a celestial symphony played one note at a time. That photon then embarks on an epic voyage across the void, for thousands or even millions of years, until it finally enters the lens of a telescope or the pupil of your eye. But its quantum story is not over. The final act of vision is just as deeply rooted in the quantum world. When that photon strikes the light-sensitive retina at the back of your eye, It interacts with a single molecule in a rod or cone cell. The photon's energy must be just right, a perfect match to kick an electron loose from that molecule. This is the photoelectric effect, the same quantum process that Einstein described. It is an all-or-nothing event. The photon delivers its entire energy package in one instant, liberating an electron and triggering a chemical cascade that sends an electrical signal to your brain. That signal is interpreted as a tiny spark of perception, a single point in the constellation you behold. The majestic spiral of a galaxy, the soft glow of a nebula, the sharp twinkle of a planet, all are built from countless individual detections, each one a quantum transaction between the cosmos and your consciousness. When you look up, you are not a passive observer. You are completing a circuit that began inside a star. You are the final step in a chain of quantum events, catching the universe in the act of revealing itself, one photon at a time. That crucial moment of inflation was not just a period of rapid expansion. It was the universe's first and most powerful sound system. The energy driving this incredible surge is theorized to have come from a specific quantum entity, a field that permeated all of reality known as the inflaton. Like all quantum fields, the inflaton was not perfectly calm and uniform. It was subject to the inherent uncertainty of the quantum world, buzzing with tiny, random fluctuations in its value. These jitters were the original seeds, the most fundamental quantum whispers of all. On their own, they were completely insignificant, smaller than a subatomic particle, and destined to fade into nothingness. But then inflation engaged. As space itself stretched at a speed faster than light, it did not simply magnify these tiny irregularities. It locked them in, stretching the quantum ripples in the inflaton field across the entire cosmos, and converting them directly into permanent differences in the density of matter and energy. The faintest hum became a deep, resonant note imprinted on the fabric of everything. Without this period of ultra-fast expansion, those initial quantum jitters would have remained microscopic and utterly irrelevant, their potential lost forever. They would have been like random static in a silent room, too faint to ever be heard. But inflation acted as the ultimate cosmic amplifier, taking that faint, meaningless static and broadcasting it across the universe with unimaginable power. It turned a quantum murmur into the commanding voice that dictated the entire subsequent history of cosmic structure, ensuring that the universe would never be perfectly smooth again. Our most precise measurements of the cosmos are beginning to disagree. Astronomers call this the Hubble tension, a stubborn puzzle at the very heart of modern cosmology. It is a disagreement about a fundamental number, the Hubble constant, which tells us how fast the universe is expanding today. We have two primary ways to measure this expansion rate. One method uses the cosmic microwave background, that fossilized light from the infant universe, to extrapolate forward to the present day. The other method uses a cosmic distance ladder, observing stars and supernova in our nearby universe to measure the expansion directly. Both techniques are incredibly sophisticated, yet they yield subtly different answers. The universe seems to be expanding faster in our local neighborhood than the early universe's blueprint says it should be. This is not a mere observational error. It is a genuine tension, a clue that our standard model of cosmology might be missing a crucial piece. The resolution may force us to look back, once more, to the quantum origins of everything. Perhaps the answer is woven into the specific statistical pattern of those first quantum whispers. The detailed properties of the hot and cold spots in the cosmic microwave background are a precise fingerprint of the early universe's physics. If that fingerprint contains a subtle anomaly, a slight deviation from what our simplest models of inflation predict, it could indicate the presence of something new. Physicists speculate that an unknown quantum field, active for a fleeting moment during the universe's first second, could have slightly altered the expansion history. This field would have left its mark on the quantum fluctuations, changing their statistical signature in a way that resolves the tension between the ancient and modern expansion rates. It is a ghost in the machine, an early quantum actor whose faint echo is only now becoming visible through the most precise observations we can make. The Hubble tension is more than a technical disagreement. It is a potential window into the physics of the first instance, a sign that the quantum whispers from the dawn of time still hold secrets that shape our understanding of the cosmos today. The spooky connection between particles does not end in the laboratory. Quantum entanglement, that bizarre phenomenon where two particles share a single fate no matter how far apart they are separated, might have written its signature across the entire sky. We usually think of this as a small-scale effect, governing the behavior of electrons and photons, but the same quantum fields that rippled during inflation could have woven threads of entanglement between regions of space that were once in close contact, only to be flung apart faster than light during that explosive expansion. This leaves us with a staggering possibility: two patches of the universe that are now on opposite sides of the sky, separated by tens of billions of light years and completely out of causal contact since the first instant, could still be quantumly entangled. Their fates were linked before the great inflation blew them apart, and that ancient connection might be frozen into the cosmic structure itself. How could we ever detect such a ghostly link? The answer may lie in the detailed pattern of the galaxies. If the primordial quantum fluctuations were entangled, the statistical correlations between temperature variations in the cosmic microwave background, or the distribution of galaxies in one part of the sky compared to another, might carry a subtle but distinct fingerprint. It would be a specific kind of harmony in the data that cannot be explained by gravity alone, a whisper of a connection that defies our classical understanding of space and time. This means the great cosmic web, with its vast filaments and voids, might not just be a structure. It could be a snapshot of the universe's first quantum relationships, a frozen moment of spooky action preserved on the grandest possible scale. The universe may not just be built from quantum whispers, but woven together by invisible quantum threads, connecting everything in a web of primordial kinship we are only just beginning to sense. This fine-tuning of the cosmos extends to the very laws of physics themselves. The fundamental constants of nature, the numbers that dictate the strength of gravity, the power of the nuclear forces, and the mass of an electron, appear to be perfectly balanced on a razor's edge. If gravity were just a tiny bit stronger, the universe would have collapsed back on itself long ago. If the force that binds atomic nuclei were just a fraction weaker, hydrogen would be the only element, and stars could never have forged the carbon and oxygen essential for life. Why does our universe have this seemingly miraculous set of rules? This profound question leads us to a final, mind-bending whisper: the Anthropic Principle. In its simplest form, it states that the universe we observe must be compatible with the existence of observers. We are here to see it, so its laws must allow for that possibility. This can sound like a tautology, but it takes on a powerful new meaning when combined with ideas like the string theory landscape. This theory suggests that the fundamental constants are not fixed and universal. Instead, they could be the local byproduct of how additional, hidden dimensions of space are folded and stabilized. In this view, there is not one universe, but a vast multiverse, a cosmic ensemble where every possible set of physical laws is realized somewhere. Most of these universes would be stillborn or barren. Some would fly apart into eternal emptiness, while others would collapse instantly. In this infinite array, our universe is simply one where the quantum dice roll at the beginning produced a Goldilocks cosmos. It had just the right amount of initial fluctuation, not so smooth that no structures ever formed, and not so lumpy that it immediately tore itself apart with black holes. This specific pattern of quantum whispers, combined with the lucky draw of our local physical constants, created the necessary conditions for galaxies to coalesce, for stars to burn steadily, and for planets to form with the chemistry for life. Our very presence, our ability to look up at the night sky and wonder at its origin, is therefore a direct consequence of that one particular quantum lottery ticket our universe received at its inception. We do not live in a special universe, but we necessarily live in one that is special enough to have us in it. The stars above are not just a gift from quantum chance, but a signature from a much wider and weirder cosmic reality. This cosmic stability we take for granted could be an illusion. The very field that grants mass to all particles, the Higgs field, might be resting in a fragile state, like a ball perched high on a hillside instead of safely at the bottom of the valley. This is a false vacuum, a temporary piece that could be shattered by a single, random quantum event. Somewhere in the vastness of space, a quantum fluctuation could provide the nudge for this field to tunnel through its energy barrier, falling into a lower, more stable state. This event would create a microscopic bubble of true vacuum. The laws of physics inside this bubble would be entirely different from our own. The fundamental constants that allow atoms and molecules to exist might be absent, rendering matter as we know it impossible. This bubble would not sit still. Driven by immense energy release, its wall would expand in all directions at the speed of light. Nothing could outrun it, and nothing could survive its passage. Every star, every planet, every structure in the universe would be instantly and irrevocably rewritten, erased from existence as the new, alien physics swept through the cosmos. This is not a fiery explosion, but a silent and perfect termination of reality as we understand it. The probability of such an event occurring in our observable universe is vanishingly small over trillions of years. Yet, the quantum nature of the process means it is not impossible, only incredibly unlikely at any given moment. The ultimate end of the entire cosmic story, the final fate of every galaxy and every quantum whisper within them, could therefore rest on a single, unpredictable roll of the quantum dice. The universe that began with a whisper could end with one. These new observatories are not just better eyes on the sky. They are time machines designed to read the faintest handwriting of the cosmos. The James Webb Space Telescope, with its infrared gaze, can look past the veils of dust and see the universe as it was when the first stars and galaxies were struggling to ignite. It will map the distribution of these infant galaxies, revealing the exact pattern of how they clumped together in the early cosmic web. This pattern is a direct descendant of the initial quantum ripples. By measuring the precise spacing and sizes of these first galactic structures, we can test the statistical predictions of inflation with a rigor never before possible. Was the pattern of those original whispers exactly as random as we think, or are there subtle anomalies hidden in the architecture of the first light? The Vera C. Rubin Observatory, with its immense rapid-fire camera, will conduct a 10-year movie of the night sky, charting billions of galaxies and tracking how their light is warped as it travels to us. This warping, a phenomenon called weak gravitational lensing, occurs because the light's path is bent by the invisible scaffolding of dark matter that lies between us and the distant galaxies. By meticulously mapping this distortion across the sky, we are essentially creating a three-dimensional map of the dark matter web. Since this web was the first structure to form from the quantum seeds, this map is the most accurate tracing we can get of the original blueprint. These telescopes are quantum archaeologists, sifting through the cosmic sediment to find the fingerprints of inflation itself. They will measure the statistical properties of the primordial whispers, the specific randomness that was imprinted when the universe was a fraction of a second old. Any deviation from the predicted pattern would be a revolution, pointing to new physics operating in that first furious moment of expansion. We are no longer just inferring the quantum past. We are preparing to read its diary, written in the language of ancient light and invisible mass. This cosmic dance of chance and law forces us to rethink the very nature of reality. For centuries, science was guided by a clockwork vision of the universe, a belief that if we knew the exact position and velocity of every particle, we could predict the entire future with perfect accuracy. The cosmos was a grand, deterministic machine, and every event, from the fall of an apple to the orbit of a planet, was seen as the inevitable result of prior causes. But the quantum whispers that seeded our universe shatter that classical dream. They reveal a foundation built not on certainty, but on probability. The specific pattern of galaxies above you, the very location of our Milky Way, was not preordained by any master plan. It was one possible outcome from a near-infinite set of possibilities, a single roll of the quantum dice that happened to produce our particular cosmic landscape. This does not mean the universe is chaotic. Its evolution is governed by the strict, predictable laws of physics. Gravity will always pull matter together, and nuclear fusion will always power the stars. But the raw material upon which these laws acted, the initial blueprint for all structure, was fundamentally random. We live in a universe where strict law and pure chance are not opposites, but partners in a breathtaking cosmic collaboration. The predictable force of gravity took the unpredictable quantum jitters and wove them into the magnificent tapestry we see today. So where does that leave us? Our existence on a pale blue dot orbiting a stable star feels both miraculous and strangely inevitable. It is miraculous because the specific chain of events that led to our solar system, and to us, was just one thread in a vast tapestry of possibilities. It is inevitable only in the sense that within a universe so vast, with so many chances, a planet like ours was bound to form somewhere. We are not the center of a predetermined cosmos, but we are a meaningful expression of its underlying principles, a testament to a reality that blends rigid order with creative spontaneity. The stars are not fixed points in a predetermined script. They are the brilliant evidence of a universe that chose one path out of many, a universe that is both lawful and free. To peer into the universe's very first instant, we must confront the greatest unsolved problem in physics. Our two most successful theories, general relativity and quantum mechanics, offer contradictory descriptions of reality at that moment. General relativity paints a beautiful picture of space and time as a smooth, curving fabric, but it breaks down completely at the infinite density of the Big Bang singularity. Quantum mechanics, meanwhile, governs the probabilistic, grainy world of the very small, but it has no way to describe the force of gravity. To understand the origin of everything, we need a theory that unites them, a theory of quantum gravity. This would be the ultimate framework, describing the cosmos when it was smaller than an atom and hotter than any star. In this realm, the fabric of spacetime itself would not be smooth and continuous. It would be quantized, composed of tiny, discrete grains or vibrating loops, a fundamental pixelation of reality. The quantum whispers we have followed throughout this story would then be revealed in their most fundamental form. They would not merely be fluctuations in a field sitting within space. They would be the very geometry of space and time itself, jittering and fizzing at the smallest possible scale. This changes our origin story profoundly. The violent beginning of the Big Bang, a singularity of infinite density, might not be the true beginning. Some theories, like loop quantum gravity, suggest that our universe could be one link in an endless cosmic chain. In this view, the Big Bang is replaced by a big bounce. A previous universe could have contracted under its own gravity, but instead of crushing down to a point of nothingness, the repulsive force of quantum gravity would have caused it to rebound, exploding outward into the expanding cosmos we inhabit today. Our entire universe, with all its galaxies and stars, might be a rebirth from the ashes of a previous cosmic cycle. The faintest echoes of that prior existence could be woven into the quantum fluctuations that seeded our own reality. Other candidates, like string theory, propose that the fundamental building blocks of everything are not point-like particles, but unimaginably tiny, vibrating strings. The specific vibrational pattern of a string determines whether it manifests as an electron, a photon, or a grain of gravity itself. In this symphony of strings, the stage of spacetime could have extra, hidden dimensions, all curled up into a size far smaller than an atom. The initial quantum jitters would then be the vibrations of this multidimensional stage as it began to expand and cool. A complete theory of quantum gravity would finally answer the question of what came before. It would reveal the true nature of the stage, the hidden geometry and the fundamental rules, before the curtains of time ever rose on our universe. It would tell us if our cosmic story is a unique, one-time event, or merely a single chapter in an infinite, cyclical epic. This controversial idea pushes at the very boundary between physics and philosophy. Some interpretations of quantum mechanics suggest that a conscious observer is necessary to collapse the wave function, to turn a haze of possibilities into a single, definite reality. In the lab, this is debated with particles and detectors, but if we scale this thought to the cosmos, the implications become staggering. It would mean that the universe's grand structures, from swirling galaxies to the planets within them, remained in a state of quantum potential until a conscious mind finally looked upon them. The act of observation, in this radical view, would not be a passive recording of a pre-existing reality, but an active participant in its final creation. You, by simply gazing at the stars, would be completing a cosmic circuit, solidifying their existence from a sea of quantum maybes. Most physicists reject this interpretation, favoring explanations that avoid such a central role for consciousness. Yet, the thought experiment holds a powerful, poetic resonance. It frames our relationship with the cosmos not as detached spectators, but as integral players. Every time we point a telescope or even glance upward with wonder, we are engaging in a profound dialogue with the universe. We are not just seeing light that has traveled for millions of years. We are bearing witness, and in that act of witnessing, we might be fulfilling a deep, fundamental requirement for reality to truly be. These quantum seeds are like the dust at the heart of a snowflake. A single, microscopic speck of dust drifting through a cold cloud is all it takes to begin the formation of an entire snow crystal. Around that humble seed, water vapor condenses and freezes, building out a structure of breathtaking complexity and beauty. The final, intricate shape of the snowflake, with its unique branches and patterns, is not random. It is a direct and detailed record of its entire journey through the atmosphere, a frozen diary of the specific temperature and humidity conditions it encountered. In our cosmic story, those first quantum whispers are the dust particles. They were the initial, random seeds scattered through the infant universe. The gravitational growth that followed, the slow, patient gathering of matter over billions of years, is like the water vapor condensing around the dust. It built up those microscopic seeds into the magnificent galactic structures we see today. And just as no two snowflakes are ever truly identical, the specific pattern of galaxies in our observable universe is utterly unique. The Great Wall of Galaxies we call home, the vast, empty void nearby, the specific spiral shape of the Milky Way. All of it is a frozen record of our universe's particular set of initial quantum conditions. This makes our cosmic neighborhood one of a kind. If we could rewind time and let the quantum dice roll again, the resulting universe would have an entirely different arrangement of cosmic structure, a different snowflake forever frozen in the darkness of space. Our journey from the quantum vacuum to the cosmic web reveals a universe of breathtaking elegance and connection. It is a story where the tiniest of events, born from pure chance, were stretched to cosmic proportions and then patiently sculpted by gravity into the celestial tapestry that surrounds us. This is not a tale of two separate worlds, one for the quantum and one for the cosmos. It is the story of a single, unified reality, where the same fundamental laws operate from the silent heart of an atom to the brilliant core of a galaxy. The universe did not build its grand structures from the top down, but from the bottom up, with the smallest of whispers meticulously crafting the largest of wonders. This profound link transforms our perspective. The stars are no longer just distant points of light. They are the magnificent billion-year echo of a quantum murmur, a direct and personal connection to the very first moment of time. The next time you find yourself beneath a dark sky, let this thought settle in. You are not just looking out into space. You are looking back in time, witnessing the final, glorious result of a chain of events that began with a random flicker in the void. Let this new perspective inspire your own curiosity about the hidden connections that shape our reality. We would love to hear your thoughts on this cosmic story in the comments below. If journeys to the edge of understanding captivate you, subscribe for more explorations into the deepest mysteries of the cosmos.